Hello, everyone, and welcome to Laser Theory and Design, undergraduate EEL 4446 and graduate EEL 5447. My apologies for not being able to be with you for the first class. There is a photonics and lasers conference going on Thursday, the day of our first meeting, that I needed to be present at, so I unfortunately needed to present to you the introduction to the course to first class in this recorded format. But it might be more preferable in some ways because you can ask me specific questions when you return and you watch it a few times or whatever. So again, this is the introduction to the course. The meeting location is in Black Hall. I've worked for this university for 23 years now, and I had to go looking for Black Hall. I thought I knew where it was, and I went to the wrong building. You probably won't make that same mistake, but nevertheless, Black Hall, 4th floor, room 415. We meet on Tuesdays, second and third period, and Thursdays, third period. In the past, what I've done for the Tuesday meeting, there's a 15-minute break between classes, so students often preferred that I cut that back to a 5-minute break and then be able to leave 10 minutes early. And of course, I'm happy to be able to do that. So when I return, just let me know, or if you want to send me an email to let me know your preferences, I'm more than happy to entertain that possibility. There is my contact information as well, my office number. You have my cell phone number. I just ask you to reserve voice calls for true emergencies, but you can text me anytime. It's still too early in the semester for me to be able to post office hours, but you know where to find me, and I'm always available by chance or appointment. I'll post office hours as soon as I know them. And all course information, everything, notes, any kind of messages is going to be done through Canvas, as I'm sure you're familiar with if you're watching this, of course. There is an optional text for the course. It's the book Laser Diodes and Photonic Integrated Circuits by Cauldron, Corzine, and Mishanovich. It's currently out in its second edition, which looks like that. This is what the first edition of it looks like, and the first edition is just as good as the second edition. Again, it's an optional text, but students often like to have a text to refer to, and my philosophy for texts is to pick one that's a good one, not just something good for the course, but something good that if you're interested in lasers, if lasers is something that you're going to want to study and pursue, and you're going to want to keep this book or either one of these books. They're both very, very good books. They're the same book, but either edition is very, very, very good. There are some slight differences in the text. For one thing, the problem numbering is different, but we'll deal with that. If you're interested in other texts, just ask me. I'm more than happy to make recommendations. In the past, I've used the book Laser Electronics by Verdian. There's a couple of chapters in Pollock's book on optoelectronics. There's Silfast's Laser Fundamentals. Lots and lots of good books. Hopefully you won't need them. The real text for the course is going to be these class notes. I give you very detailed notes. It's almost like a textbook. Perhaps the words aren't there, but almost as good. Okay, so if you want something supplemental, though, these are very good references. The Corzine and Cauldron book is a very good one to be able to refer to. The only official prerequisite for this course is the physics of EEL 3008. And I've completely revamped the course to take that into account. In the past, our curriculum has changed a few years back, and in the past, electromagnetic fields, EEL 3396, and solid-state devices, EEE 3472, I believe it is, 3396? No, 3472 is Fields, 3396 is solid-state, right? Used to be required classes. They're no longer required classes. So a lot of that material got condensed into the physics of EE. You don't need even to know, let me put it, even though that's a prerequisite, you don't need to know necessarily the material in physics of EE at a very deep level, because I'm going to cover all that. What I will expect you to know is to be reasonably comfortable with, the ideas of vector calculus and physics 2 and so forth, and courses you've had in the past, ideas from circuits or signals and systems, and the background material, okay? I will cover everything that you need for the topic at hand. In other words, I won't say you learned this in 3008, so you should know. I won't do that, right? What I'm really looking for by having you take 3008 is a certain level of, shall I call it, academic maturity. I don't want you to be seeing any of this for the very first time. I want you to have seen it before. The nature of this material is such that the more you see it, the better you learn it. I've been studying this stuff now for more years than I'd like to say. And still, every time I read something new, I'm learning more. I go deeper and deeper and deeper. So that's it. That's all I'm looking for. I'm going to take you and lead you through the material that you need without making any assumptions other than the most basic background that every engineer ought to know. The topics to be covered are roughly seen demonstrated here, shown here. I think I got a little overly ambitious when I said semiconductor photodetectors. I don't know that we'll be able to get that far, but I'm pretty confident that we'll be able to cover everything that you see here. And that's quite a bit of material as it stands. The course is taught at the graduate level. I'm getting a little bit ahead of myself, but the university requires that I make a distinction between graduate students and undergraduate students. So there is an administrative distinction in a certain sense between that. As far as the instruction goes, the instruction is going to be identical. As far as what I expect you to know goes, it's going to be identical. In my mind, there's very little difference between an advanced undergraduate and a beginning graduate student. So to try to say to make a distinction is not really something that makes any sense to me. I'm going to try to make the course as pleasant and enjoyable for you as possible. There will be homework graded 0 to 10 worth 20% of your grade. I'll talk about the homework policy in a minute. Now, pay careful, and that's both for graduates and undergraduates. Pay careful attention to this. Class attendance and participation, 30% of your grade. Wow, that's a lot, right? That's a lot of a lot of score. What does that mean? That means I want you in class. That means I feel that the classroom dynamic, the interaction, the exchange of ideas, the comments made among your fellow students and me is very, very important. So what I'm going to do is, once this is airdrop, and I know people are shopping and so forth, so once the things settle down as far as who is in the class, I'm going to make tent cards with your names on them, and I'll give them out at the beginning of class and collect them at the end of class. And that way, during within a very short time, I'll be able to learn all of your names and so know who you are. There are no tests per se. Again, I want to take some of the pressure off of you, but there will be quizzes, short quizzes, roughly 10, give or take. And they're going to be 5 or 10 minutes in duration. For the graduate students, they're worth 20% of your grade for both cases. For the graduate students, I don't drop any of your quiz grades. For the undergraduates, I'll drop the 2 lowest quiz grades. Okay? Then the graduate students will either, depends how, we'll play this a little bit by ear for now, you will either write a paper or make a presentation on a selected and approved by me, topic in lasers. That's worth 10% of your grade. Undergraduates are going to have to write a critique of one of those papers. And again, papers are published. You could take an abstract and repeat an abstract or a summary. That's not what I'm looking for. I'm looking for to demonstrate your understanding, whether you're a graduate student presenting the topic or whether you're an undergraduate that is explaining what the graduate student presented. It may require you go and study the paper a little bit, but I want you to see that you're going to be able to read the literature once you get pretty well into this course. And then there will be a final exam worth 20%. I have to do that because department requirement is that I give a final exam. That's just a department policy. It's going to be probably stay a reasonably small class, so there's a good chance that exam could be oral. We'll schedule a time when you'll come in and I'll ask you some questions, or if you prefer, or if maybe it works better, we'll have to see how that goes, a written final exam worth 20%. Of course, needless to say, I shouldn't even have to say it, but I guess officially I need to, that there is zero tolerance for any sort of cheating, right? Cheating is just not consistent with a learning environment. The policy on the homework, I'll assign homework, and it's due 1 week after it's assigned, for the most, unless otherwise stipulated. And the deadline for submission is 5 p.m. of the day it's due. Important here, I will not answer any first-time questions on the homework on the day that the homework is due. I am not going to give you tons of homework. You're not going to be getting 10, 20 problems a week. None. You're going to be getting a couple of problems a week, maybe. But those problems are carefully designed or chosen by me so that I think you will learn from them. You're probably going to have questions. You're probably not going to be sure in every instance, not always, but in some instances, you may not be sure how to do them, and you're going to have to ask me questions. I like that. You know, I want you to be able to ask me questions. I want the homework to be a learning experience. That's why, if you want to wait until the day the homework is due and say, I better get this done, you're on your own. You can't come to me for help. Okay, so that's the policy there. I used to be very flexible with the submission of the homework, but it was your predecessor students' requests that I make hard, firm deadlines so that you don't procrastinate and put it off. So after 5 p.m. and up to 1 day late, there would be a 25% reduction. 2 days late, a 50% reduction. 3 or more days late, a 75% reduction. It's always worthwhile getting it in because you could always get up to 25%, no matter how late it is. Okay. I expect a certain degree of professionalism for you, so on your homework submission, neatness counts. I'm not happy when somebody hands me homework that's scribbled to the point where I could barely read it. The paper has been erased so many times that there's a hole in the paper practically, but then somehow, boom, magically the right answer appears, If that happens, I might just call you in and say, show me how you did this. I don't get I don't understand what you did on the paper here. Neatness counts, in other words. Electronic submissions for the homework are fine and in many ways encouraged, right? Whether you give me your homework on paper or electronically, or whether you upload it on Canvas, or whether you email it to me, or whatever you do, please use the following format. If you do it by hand, on the top of the page, write your last name and then laser homework number 1, 2, 3, 4, whatever. If you're going to submit electronically, name your file with your last name and then laser homework and the number of that homework, okay? Because what I tend to do is when I collect them all and I drag the file into a folder, and if your file is not named properly, I'm not sure what I'm looking at. So please follow this naming and numbering format for your homework when you submit. Again, this might be repetitive, but that's okay. On all the work, neatness and clarity of presentation, in other words, professionalism counts. If you were giving something to a boss, you wouldn't scribble it on the back of a piece of loose leaf torn from a notebook. I really don't like when you do that here. plots, I say plots and graphs must be done using a computer. They really should be done using a computer unless there's some extenuating reason for not doing so. If a preparation of your homework is poorly prepared, I have the discretion of taking off points for that. And for our quizzes, the 5 to 10 minute quizzes that we'll have roughly 10 of during the course of the semester, there's a time limit that I strictly enforce. There seems to be inevitably every so often a student who feels they deserve more time than everybody else, and even when I say stop writing, you keep writing. If you do that, you risk getting a 0 for that quiz. Okay? There could be more than one quiz per week. A quiz might be repeated if the results warrant. In other words, I want to see, my goal is to see all of you learn and do well. That's what I want to see. Right? So if we take a quiz and most of you bomb out, I might just give you that same quiz again. So if you bomb a quiz, it might be in your best interest to figure out why you bombed and get it right and know how to do it, because you're going to walk into the next class and there's going to be either the exact same or a very, very similar quiz again, right? So, and of course, missing class doesn't excuse you from knowing what was covered. If you're absent, ask your classmates what was covered that day. If need be, talk to me. Things like they want you in class. A big part of your grade for the course is your attendance in class. So things we say in class are potential quiz material. There is no official text, and the notes, I don't know if you're going to print them out or not. Some quizzes may be open note, open book, or whatever. Some will not. We'll work that out as time goes. Okay, how we do that with online, PowerPoint thing like this, we'll have to figure out as we go. If for whatever reason you would like a printed set of notes and don't have the wherewithal to do that yourself, talk to me. I might be able to provide that for you, but I'd only do it on request. My bottom line goal is for you to learn a lot and do well and have this be one of the best courses you've taken at UF. Okay? I don't want to say the best. That might be too arrogant of a statement on my part. But don't be afraid to critique me. I remember the person who taught this course before me was Professor Zori, who has been retired for a number of years now. I don't know if any of you remember him. But when I first started teaching the class, I was talking to one of a student who took the class from him, and he made the comment to me that he thought that the laser class with Professor Zori was the best course, or maybe he said one of the best courses that he ever had at UF. And that's my goal too. Yeah? I want you to learn tons of stuff from this course and enjoy doing it. Don't be afraid to critique me if you think I'm not achieving my goal. It's important for you to tell me. Don't be afraid, but you don't have to be afraid. Course evaluations, what are we, 30% success rate on those things? Most people don't fill out course evaluations, right? That means you're probably happy, I guess, right? But that's too late, right? The course is over by the time you do course evaluations. So you could talk to me anytime. I for the first time, I discovered this website, sayat.me. Okay, that's the link right there, http://sayat.me. It's going to ask who you want to talk to. You type in my name just like that, all lowercase, no space, okay? And it allows you to make anonymous, instantaneous comments to me. I'll get an email with your comment right away. And I won't know who you are unless you sign your name to the note, of course. But you could tell me something, and I have no idea which one of you is saying it. Right now, I have the switch set to keep the comments private. I'm just as happy to make them public. So everybody gets to, if you make a comment, everybody gets to see it. Okay, and I guess you get to see my answer or whatever. So however that works. But try that out. Let's see how this works. As I say, this is the first time I'm using it, and it perhaps gives us some instantaneous feedback. This is just boilerplate. The university requires that I tell you what's an A and what's an A minus and so forth. Believe me, you're going to be happier with what I'm going to do. Okay, but I got to tell you something, and so that's what I'm going to tell you. Again, let me just emphasize what I said already, that the course, it's only fair, of course, since there are graduate students in the room, that the course be taught at the graduate level. And once again, to my mind, there is little difference between a beginning graduate student and advanced undergraduate students. And so what it requires, the real prerequisite for this course, is an intellectually mature attitude on your part. The only distinction, there won't be any distinction in the level of instruction. The only distinction between undergraduates and graduates is in the grading policy that you know. And I've made it so that seeing the material in EEL 3008, what our course here at UF that's called Physics of Electrical Engineering, as well as what you've seen in previous coursework, is all that's expected of you. And again, I don't even expect you to know and remember what you learned in 3008, but that you've seen it before, so it's not just hitting you for the first time. The best way to do well in this class is to study, to keep up, and to ask lots of questions, preferably during office hours. I've taught this course now for a number of years, as well as the corresponding course in photonics. I've had many students that have fallen in love with this subject and have gone on to go on to for careers in photonics, with Intel Photonics and so forth, or gone on to get PhDs in photonics and lasers and so forth. And one characteristic of the students who really did well and loved this course is that they were in my office all the time, always coming in to ask me questions so that they could understand the material at a deeper level. If you want to be a good student, there's no secret to any of that, right? You study and you come and you ask questions and just try to understand it. Always ask why. There's a etiquette in the classroom. I want you there, but I don't want you there doing homework for the upcoming class in a period or two, right? When you're in class, you put away all distractions, all reading materials, cell phones, tablets, computers, unless you're using your tablet or your computer to follow along with the slides, like these slides, for example. But I want your attention to be on the lecture material, right? Active engagement during class is expected. Again, as I said, material that we discuss in class could be potential quiz material. I mentioned already I'm going to use 10th cards with your names on them so I could quickly learn your names. Everybody loves getting extra points. Everybody's saying, I want to get that. I want to make that cut. I don't want the B plus. I want the A minus. I want the A, right? So being on time for class, being engaged in class, diligent on the homework is how you make me happy, and I'm willing to bend over backwards to help you do well in every way I can, as long as you're showing me the effort that you really want to learn this stuff. There's, just for handy reference, a calendar. You probably know this already. Sadly, we don't have any days off until Thanksgiving. That's a long stretch, but I'm hoping we're going to have fun, so it's not going to matter. We'll look forward to Thanksgiving, though. We all do, right? Don't be afraid to make mistakes. I don't mind mistakes. I make tons of mistakes. Believe me, you'll see me make mistakes. As this says in the cartoon, if we learn from our mistakes, then we should make a lot of them. One thing that's good or bad, I don't know. You tell me. Is I've completely revamped this course, completely different from any way I've taught it before. And I think I said it's because I'm in my mind I'm saying, okay, now just EEL 3008 is your only background. So and I'm very happy with the product that I've produced. I'm going to hope that you agree, but you're the guinea pigs at the same time, right? So there's going to be mistakes that I've made, and please don't be afraid to tell me. I do make mistakes, and how are those mistakes caught? Most of the time, sometimes I catch them, other times you catch them. Other times you say, look, Professor, this should be a factor of 2 and you forgot that. Yes, exactly. So please tell me. I'll let you read this. It's a bit of a philosophical note. What are the things that I think are hurting us in our profession in a certain sense these days? Are people think very often that they don't really need to know anything because they could Google everything. To a certain extent that's true. You could look up anything instantaneously. That's marvelous and so forth. But that's information, and information is different from knowledge, right? Anybody can go to look something up on Google, but do you really understand what you're looking up on Google? And the only way to understand something is to immerse yourself in that information for an extended period of time. Then comes knowledge, right? And that's really what we're seeking, is knowledge. That's what experts are. Experts are subject matter experts. They have the knowledge to understand the wealth of information that anybody could look up. And I've seen, I without going into it now, this is not the time for it, I've seen people embarrass themselves because they need to know something and they don't, and they go to Wikipedia and they look, and Wikipedia is wrong, and then guess who looks like a fool, right? So always remember there's a difference. There's even this pyramid, the data, there's tons of data out there, facts and figures that tell you things. Information happens when that data somehow gets categorized and contextualized and so forth, but true knowledge only comes when you immerse yourself in that information, understand what it's really saying, and that's when you start to move toward being the subject matter expert, which is hopefully all of our goals. I always like to post, I don't know if any of you know Professor Sheplack. He's really in the mechanical and aerospace engineering department, although he has a 50% appointment in electrical engineering as well. And he always gives his students, and I like this, it has to be modified a little bit because our course is kind of different, but he has this 5 times strategy to help you learn in the class. That's when you see the material 5 times before you're expected to know it in an exam, in a final exam, a quiz or whatnot. The first time is probably the hardest time. I know I'm no different than you, really. We're all the same, right? The first time is when you perform your reading assignment before class. You're going to have the notes posted, and I know this is the intentions are good, but for all of us, we're all so busy. One of the best things you can do is read through the notes before class to see what I'm going to talk about. Boy, does that set you up for understanding what's happening in class. Once you get that done, the second time is when you see the material in lecture. Then things hopefully really start to click. The third time, I don't know that is going to really apply directly to here. He says when you rewrite your lecture notes to include the material from the lecture, the reading assignments, and so forth. My notes, my slides that you're going to be seeing here are very thorough, very complete, but I don't go through every little last step. Although you have it, I might say, this is the equation we need to solve. You know how to solve it. The solution is on the next page, and let me just jump to the answer, right? It's going to be on you, if you don't know how to solve it, to look at the stuff in between, those in between slides, and fill in the steps for yourself, right? So that might be the equivalent here. And the fourth time is when you do your homework. You see the material a fourth time then. And then finally, the fifth time is when you study for exams, So, it's what is it saying, really? It's saying the more times you look at it, the more times you read it, the more times you do it, the better you're going to learn it. So that's advice from Professor Sheplack that I like. The bottom line is study. That's the best way to do well in any class, is to study. In terms of what we're going to be talking about in terms of lasers, talking about Google, I went to Google Images and I looked up electronic oscillators. And I found a zillion of them, of course. And here are 3 electronic oscillators. Okay, an FET one, a BJT one, and a op-amp one. I don't know, if you looked at this, would you have known these are oscillators? Maybe, maybe not. There are a couple of clues. One clue is that there's no input on any of these circuits, right? I don't see any input voltage or anything like that. Of course, there are power supply connections. You gotta plug it in, right? You gotta put in batteries in. You got everything. You can't get something for nothing, right? So if you're going to make an oscillator, that signal is going to come from somewhere, and it's going to come at the expense of your power supply. But other than that, there's no input. Yet there are outputs. Here's an output. Here's an output. This doesn't have an output, but it looks like it has an 8-ohm speaker. So that's an output, right? I look at this one and I see this tuned circuit, this parallel LC circuit. That might be a clue that it's some sort of some sort of oscillator. You might say tune the amplifier, though again there's no input. So here's what's being amplified. The point here is that electronic oscillators are complicated. Lasers are oscillators, but they're very, very simple. Any oscillator, in principle, here's a block diagram for any oscillator. It doesn't matter whether it's an electronic oscillator or a laser oscillator, or for that matter, even a mechanical, whatever. You have some sort of gain, amplification, you have some sort of feedback under the right conditions, and you have to use a power supply to power it up, and the word in the jargon of lasers we would say we have to pump it. In a sense, maybe there is an input. What seeds any oscillator is noise, except of course you don't usually show that. Noise is always present. If it weren't for noise, oscillators would not be self-starting. Okay, but that's the general idea for an oscillator, an electronic oscillator or a laser oscillator. Gain here, a gain path, and then a feedback path, an appropriate feedback path. A laser oscillator, and as I say, it's the simplest oscillator of all, is this. You have a gain material. We'll have to look at what that means. How do we do that? What gives us optical gain? Of course, you don't get that for free. You got to pump it, pump it somehow. You could pump it with an electrical signal. You could pump it with an optical signal. You could even do, in some cases, chemical pumping. I'll show you some examples. There's feedback. Well, here's the feedback. It's called a cavity. Right? There's noise inside this thing, and the noise is going to be optical noise. It's going to spit out photons, right? And these photons are going to bounce back and forth inside this cavity, and we'll have to look at this and see under what conditions we get sustained oscillation. So we have an oscillator. The cavity in this case, I have a mirror here that reflects all the light. At the front end, I have, let's say, a 99, I put 9, just made that up, a 99% mirror that allows some of the light to leak out. That's, in essence, what you see here is just about every laser in one way or another. There are some variations, but still, they all kind of boil down to this. The lasers we are going to study are as follows, or here's what we're going to study and what we're not going to study. We're going to start with some laser basics. I want to give you some top-level information and analysis and design of lasers that apply to any laser whatsoever. That's important, right? So that you'll have enough to, when you branch into a new area, you'll be able to understand what's going on, regardless of how it's being done. We'll talk briefly about solid-state lasers. And you'll find out what those are too, because what I really want to do is I want to spend the bulk of the time during this semester on semiconductor diode lasers, because these are the workhorse in many cases for electrical engineering applications, and this is such an active area. There's research being done every day. These things are getting better and better and better and more efficient and more powerful, and they're starting to replace more and more of the other kinds of lasers. There's solid-state lasers, which we'll talk about. Certainly there are gas lasers, which are these big, you may have seen one in your high school. I'll show you a picture of a helium neon laser. There are chemical lasers, which are really rare. I'll just tell you what they are. There are fiber lasers. If we have time to talk about them, I will, because one thing good about a fiber laser is you can get lots of power out of them. You can get hundreds of watts. But they're going to talk about laser basics, and then we're going to jump really to semiconductor diode lasers. Here's the first ruby laser. Look how simple, really, when you get right down to it. There's a ruby rod here, and wrapped around it is this quartz flash tube. It puts out this bright burst of white light, right? And that's what's being used to pump the quartz crystal, the ruby crystal, raise its atoms to a higher energy level, and when those atoms spontaneously fall back down to a lower energy level, they emit light. There are a couple of mirrors here that form the cavity. You see over here it says there's a 100% mirror, and then over here there's a 95% mirror, so light gets out of this thing. This is the necessary power supply to drive the quartz tube. That's it. That's the whole laser right here. Really very, very simple, right? I mean, the physics behind it is what we're going to have to study to a certain degree, but really conceptually it's quite simple. Here's another solid state laser. This is a ND YAG. YAG is it's a crystal. It's yttrium, aluminum, and garnet, and it's doped with neodymium atoms. A lot of what happens in lasers has to do with finding the right material. So in many cases, you could say we depend on and work closely with people in material science and engineering to find the right combination of materials to give us, that's really what it's all about, that it's transparent at the wavelengths we want, that we could pump it readily and get gain at the wavelengths we want, and all that kind of stuff, So this is a far more sophisticated but very fancy neodymium YAG laser. Diode pump, that means you have to pump it somehow. You're pumping it with an LED, okay? Or maybe another laser, as the case might be, it depends. These tend to be expensive, right? Often they're used in medical applications because they're very, very narrow line widths and so forth, and they again can be very high power. Here is an old-fashioned, I call it old-fashioned, I don't know, a Heaney laser. Maybe you had one in your high school or something, right? It's a tube filled with helium neon gas. Here's a 100% mirror. Here's a partially reflecting mirror. You can see the laser spot projected on the screen down here. This is the power supply that is used to excite the helium neon atoms inside the gas. The two mirrors form a cavity and it lasers. In a certain sense, Mother Nature is on our side when it comes to lasers. They just want to work. It's easy to make a laser, it's hard to make a good laser. So that's kind of what we're going to be studying. Here's a chemical laser. These are rare because they're actually very dangerous. They could produce very, very high power. And the pumping process is coming from a chemical reaction inside so you're pumping this with some sort of gas, and when the two gases actually, and when those gases combine, the chemical reaction gives off light, and you have mirrors in here, and again it's a cavity, so you get lasing. These are used for high power industrial applications. This is a retired Air Force project now. The fuselage of this plane was a chemical laser, and then the beam came out of the optics on the nose of this plane. This is a coil laser. Coil stands for chemical oxygen iodine laser. One of the problems with it is the byproducts of the chemical reaction are some of the most toxic substances known to man. You wouldn't want this plane flying over your neighborhood, So this is kind of an obsolete idea, but it's a super duper high power laser. Nowadays, a lot of this is being replaced with the fiber lasers, hundreds of watts of fiber laser. Here's again, laser being used for electronic warfare applications. We're not going to talk much about that, but that's one of the applications of lasers. There's also fiber lasers. Remember I said if we can, we'll talk a little bit about them, maybe more in terms of the walking you through them in terms of a homework assignment. What you do is you take ordinary optical fiber and dope it with a rare earth material known as erbium to give it the properties that you want. Now this picture is not taken with an ordinary camera. This is taken with an infrared sensitive camera, so these usually produce light in the infrared, so you can't see them with the human eye. But because the gain is distributed over the entire length of the fiber, you could generate lots of power. Things aren't centralized to a small little area. The way it works is you take it varies, but let's say 100 meters of EDF is erbium doped fiber, and what you want to do is make a ring. There's your cavity. It's not a cavity with mirrors, but the ring itself is a cavity. Okay, the light comes back around in phase with itself, and it's just like a cavity. There's an isolator that keeps light going in only one direction and gives high attenuation to the opposite direction, and that's because otherwise you'd get standing wave patterns being formed and so forth. You pump this erbium fiber with another diode, and this is a wavelength division multiplexing coupler. So this allows this wavelength to get in, and it's designed to work with two different wavelengths. You have the wavelength of the laser and then the wavelength of the pump, and you want to separate those two. You need a polarization control because often this is polarization sensitive, and to get light out of it, instead of having like the 95% or 99% mirror, you have an output coupler. OC stands for output coupler, and that takes, let's say in this case, 20% of the light, and that's the output of your laser. And again, since the power is generated, the laser intensity is generated over what might be 100 meters, you could generate a lot of light. So the output power of these things could be rather large. Here's a packaged one. This is what it might look like with the fiber output coming in. You got to hook up power to it, and as you see a connector here to be able to hook up the necessary controls and so forth. But the bulk of what we are going to study is going to be this. It's going to be the semiconductor diode lasers. Okay? They're small in size, so they're limited in power in that sense, right? This is a laser chip, and here's one sitting on the head of a pin. Okay, so the laser itself might be rather small, but you got to package it up, and so now the packaging gets bigger. This might be 1 inch or something like that. And then this just doesn't work by itself. You have to power it and so forth and control it, and so this is a laser driver. Generally this chip you see gets mounted here in a laser driver that does the various things that need to be done. What are all these pins? Well, for example, 2 of them are the laser diode itself. Okay, pins 10 and 11 is the connection to we would put the current to drive the laser. The pumping here is done with an electrical current. You might these are very temperature dependent, so you want to control the temperature. So there's a thermistor here, and that thermistor goes to a couple of pins, because what you do is you calibrate this, you measure the temperature, and this laser is mounted on a TEC. A TEC is a thermoelectric cooler. You put a current in this and you're able to control the temperature, so you keep your laser at a constant temperature. There's a monitor diode here, which is a photodetector, which is looking at some of the light that this laser produces for 2 reasons. One, you know if your laser is working or not, and secondly, you may want to be able to, there could be a mode where you want to make sure you keep the power constant, right? So this could be used as a power monitor, so your laser is always putting out whatever it is, 100 milliwatts or 50 milliwatts. So that's what all these pins are for. Obviously not all of them are used. As I say, this is becoming more and more the workhorse of the industry, and this is going to be what we spend a lot of our time looking at. Here's another picture of the chip itself. Basically what's going to happen is the pumping is going to take electrons from the valence band of a semiconductor device. It's going to raise it to the conduction band. Those electrons thermalize to the lowest energy, and they drop from the conduction band to the valence band. When they do that, they give off that energy in the form of light. So it's as simple as that. Simple, but not so simple, as we'll say. You pump it with a current density. It's they're a p-n junction, so there's a p material and an n material, usually separated by a region of intrinsic material, either undoped or very, very lightly doped, is how this works. Here kind of gives you more of a cartoon of how it would look. You have an electrical lead here and a metal contact, and of course, Another metal contact on the bottom here. This could be the heat sink as well as the thermoelectric cooler. You have an N-type and a P-type, and the active region is what produces the light. You often put in these silicon dioxide insulating materials to control the shape of the current density, the flow of the current density inside the junction, so that you're able to keep track and control of the part of the laser that's lighting up for you, so to speak. There is a cavity. There are no mirrors per se, but the cleaved facet of the crystal, it works as a beautiful mirror, and that cleaved facet, it's about, for some materials like gallium arsenide, it's about a 29%, 30% reflectivity. That's enough to form your cavity, light bouncing back and forth, and here's the output. Because of the odd shape of this is a skinny and long. In the skinny direction, it's like a point source. The beam is very wide. In the wide direction, the beam will be very narrow. So the output of this kind of a laser is usually an elliptical beam, which you could fix up with external optics, make it look like whatever you want it to look like. So in this narrow direction, you get a good quality kind of Gaussian mode for a beam. In the broad direction, you get a poorer quality, higher order Gaussian modes. We don't have to worry about any of that for now, but I just wanted to give you an idea, right? As far as sizes go, typically this might be 10 microns wide and 250 microns long. Before this course is over, we'll understand why 10 microns, why 250 microns. This active layer here might be anywhere from 2 or 3 nanometers up to maybe 150 to 100 nanometers. We'll understand why that is as well. Typically, the drive power to power this thing up is 150 milliwatts, and a typical output power might be 50 milliwatts. Now, this is all the kind of thing that we're going to be studying. We're going to study this kind of device in great detail as we move forward. So for semiconductor diode lasers, the output beam is elliptical. We're kind of indifferent about that. It's okay, we could deal with that. It's not good, it's not bad. And there's in that one direction a large beam divergence. Again, not good, not bad. The gain curve, the width of the curve where you get the bandwidth of the optical amplifier could be huge. It could be up to 100 nanometers. That's huge, trust me, compared with other types of lasers, and we like that. We could take advantage of that, as we'll see. A broadband amplifier, right? It doesn't take much to understand that broadband amplifiers are good things. The optical gain is huge, enormous optical gain, larger than any other laser, which is why we can make these things so small. And maybe the one bad point we'll put on our unhappy face is that the spectral purity is not as good as a gas or a solid state laser. But again, this is an area of active research, and it's getting better and better and better every day as the day goes on. A lot of what we do is dependent upon the materials that we use to make the laser. Again, we have to look a little bit at material effects and material selection, but that is not the focus of the course. We assume that someone has done a lot of the preliminary work and they hand us the laser materials that are best used, and I'll give you an idea of what I mean by that. But certainly the lasers are generally compounds that come from the 3-5 columns of the periodic table. So things like aluminum and gallium and indium from group 3, and things like phosphide and arsenic and so forth from group 5. You alloy these things, and that's how you make a compound material that's used for a laser. So we'll take a look at the whys and the what fors for all of that to a certain extent. The reason you worry about materials is the material really decides what wavelength you're going to emit. So for example, if you have an indium gallium nitride laser on a gallium nitride substrate, there's the wavelengths that it tends to produce, okay? And these are used for example, for data storage. These are getting up into the blue or the ultraviolet here, okay? There's aluminum, gallium, indium phosphide lasers on a gallium arsenide substrate. Again, they tend to be indivisible. The visible spectrum is from about 400 to 700 nanometers, so these lie in the visible spectrum, and these are what are used for laser pointers and DVD players. Now we start to move more into the infrared with aluminum gallium arsenide material and a gallium arsenide substrate. These are used for CD players and laser printers, pumping diodes for solid state lasers, and they emit in that wavelength band. Now we really get into the infrared, longer wavelengths. We have indium gallium arsenide on a gallium arsenide substrate. Again, these are used for pumping lasers for the erbium doped fiber amplifiers. That's what EDFA stands for, erbium doped fiber amplifier, like the fiber laser I showed you, and other fiber amplifiers. High power VCSELs. We'll look at VCSEL. A VCSEL is a vertical cavity surface emitting laser. And don't worry about that now. We're going to study those things. And then finally, I highlighted it in yellow because in the infrared, in the 1000 to 1650 nanometer regime, that is the workhorse for our optical fiber telecommunication background. That is the basis for our telephone conversation. The communication in the world, which happens on optical fiber, is happening either at one of two wavelengths, 1310 nanometers or 1550 nanometers, for reasons we'll discuss. I'll tell you why later on. Let's not worry about it now. These are the workhorse for fiber telecommunication, and these are made with indium gallium arsenide phosphide, a quaternary compound, right? Compound laser on an indium phosphide substrate. So that's why materials are important. Different materials give you different kinds of, give you different wavelengths. What we are going to do is we are going to start with a general study of atomic systems so that we could understand how any kind of laser works. We're going to kind of look at a generic class of laser theory that work just as well for solid state lasers or gas lasers or semiconductor diode lasers. But then we're going to move into the electrical and optical properties of semiconductor materials, and then look at how the photons and electrons and holes interact with each other in a semiconductor. Then we're going to look at LEDs, light emitting diodes and lasers, and what we need to do to design them to meet certain specifications. One thing we are not going to do is we are not going to consider fabrication technologies, because we have separate courses in this department on that. So if you want to learn about fabrication, there are plenty of opportunities to do so, and this course is packed as it is, so we're not going to worry about trying to pack anymore. In terms of motivation, it's here, but I'm not going to play it here. This is a video put out by Hewlett-Packard Research entitled Photonics in 4 Equations. It's posted in the files. It's so well done. If you want to see what's important about photonics and lasers and where this field is going and how a major player like Hewlett-Packard is involved in this, it's something you're going to want to watch. I put this more for humor. We all know Lord Kelvin, the famous temperature, degrees Kelvin sort of thing. In 1900, he gave a speech saying there's nothing new to be discovered in physics. All that remains is more and more precise measurement. Oh, how you better be careful what you say. This was just before the explosion of quantum mechanics, and oh well, he's going to go down in history for being known for degrees Kelvin, and probably this gets quoted a zillion times. Poor guy, right? What I'm interested in, what we're going to do is what good old Dr. Einstein said: scientists investigate that which already is, engineers create that which has never been. So we want to do both. That's our goal, is to do both. So that's pretty much all I have to say to you for now. Again, my apologies for not being present for the first class. If you have any questions, you know how to reach me. You could email me. You could text me contact me anonymously at that sayat.me website. Send me a question on Canvas. Do whatever you want. If you have any questions when we meet in person on Tuesday, I'll be happy to answer them. In the meantime, thank you, and I look forward to getting to know all of you. Bye-bye now.